Okay, let's look at every areas of rectangles that have the same perimeter. So we're going to look at different areas even though we have the same perimeter. Pretend we have a rectangle that has a length of 105 and a width of 70. Let's give the length and the width of a rectangle that has the exact same perimeter but has a smaller area and has a larger area. Okay, we need a smaller area and we need a larger area based on the constraints of a length of 105 and a width of 70. So this is a non-picture geometry problem, so it would be a good idea maybe to draw a picture and to try to understand what's going on. So a rectangle looks kind of like that. Length is 105 and width is 70. Right? So it's like a field or a pen that's enclosing something. 105, 70, 105, and 70 all the way around. Now, the naive way to approach this would be to maybe calculate what the perimeter is, work with that, but since the perimeter has to be held constant, that means that the length and the width have to be the same sum no matter what, total of 175. So 105 and 70 have to add up to 175, and the other dimensions, because it's a rectangle, are always going to be the same. So the question really boils down to is what can we do to this picture to give it a larger or a smaller area? So on the most extreme example, consider a rectangle that was really skinny but really long. That could have a really large perimeter but have an extremely small area because you could make it be essentially infinitesimally skinny. On the other hand, if you made it as square-like as you could, then you would be enclosing as much area as you possibly could. To prove this is not difficult, but it takes a little bit of calculus, so you have to go a little bit further than an algebra class. But square figures enclose, or rectangles that enclose the most amount of area for the least amount of perimeter, and in order to make it extremely small area, just elongate the rectangle to make it as skinny as you possibly can. So remembering the dimensions of 105 and 70, let's go to the next page. The initial dimensions were 105 by 70. Let's give ourselves a smaller area by making our rectangular region be skinnier, elongated in some sense. So I got the 105 and I got the 70, and I want to make it even more extreme. So I'm going to take the largest number, which is the 105, and I'm going to make it even larger. 115, I made it larger by 10. And I'm going to take the small number, which was 70, and make it smaller by the same amount, 60. So in the picture, it's like I took the 105, made it longer, and I made the 70, and I made it smaller. So I'm making myself a skinnier rectangle. So what's 115 times 60? Well, 0, placeholder. 6 times 5 is 30. 6, 1, 9, 3. Or adding the 3 gives you 9, and then 6. So it looks like 6,900. So the dimensions of 115 by 60 give you 6,900. Okay, on the other hand, the larger area was going to be more square-like, so the dimensions would become closer to each other. So instead of going more extreme, 105 is higher than 70, so let's make it less extreme. 105 minus 10 would be something like 95. And then where do we compensate? Well, we bring that extra 10 and move it to the other side. So the 70 becomes an 80. What's 95 times 80? Well, 0, placeholder. 8 times 5 is 40. And 9 times 8 is 72, plus 4 is 76. So here we have a larger area. So these would be the dimensions of a smaller area, and these would be the dimensions of a bigger area. Just to compare it, just to make sure, let's take the 105 times 70 and make sure that the smaller area is smaller and the larger area is larger. 105 times 70 is, placeholder, 35, 3, and 7, right? 7,350, and 6,900 is lower than 7,350, and 7,350 is lower than 7,600.